I want to talk about probably the number one theorem that you have been using in the past, but you maybe not knowing why you can use it. Okay, we haven't talked about it yet this year in detail, but it is the Pythagorean theorem. What is the Pythagorean theorem? Good. A squared plus B squared is equal to C squared, right? Okay. Just kind of give you a little bit of like history background, and this happens a lot in math. So, like a long time ago, when Pythagoras was alive, so we're talking centuries ago, like the cool thing to do, the upper echelon of society, the top people in society were thinkers. They were philosophers. They were mathematicians. They were, those types of people. Okay, society changed a little bit, and now when you think of like upper echelon society people, you guys probably think celebrities, LeBron James type people, that kind of stuff, right? Okay, where I wish it was more like we're thinking of like upper echelon people like Warren Buffett, maybe Jeff Bezos, those types of people, because they're the ones that are really influential in society. Does that make sense? Okay, but we kind of gravitate towards your celebrities, your movie stars, and your artists and that kind of stuff, your athletes. And back in this time, those types of people that the society kind of gravitated towards were people like Pythagoras, Aristotle, Gauss, all these, Newton, okay, and he wasn't all that long ago. But that was the thing to do. That was where the money was being made. Does that kind of make sense? So these people like Pythagoras, he had like so you have like, you think about like artists or athletes, okay, they have fan groups, right? They have cronies, that kind of thing, right? Okay, people that follow them. Now, the people that follow them usually don't do the same work that those people do. So if I'm a big LeBron James fan, I don't go out and play basketball every day, okay, and I don't contribute to his skills, okay, but back in the time when Pythagoras was doing work, he had followers, okay, and what was a little bit different is that those people actually contributed to his work, all right. So when we talk about people like Aristotle, Pythagoras, these influential mathematicians and scientists and philosophers throughout history, they had followers. They had schools of thought. Like Plato had an entire school that was of followers that was attached to it. Does that make sense? And their thoughts and a lot of their things that they came up with actually get contributed to, say, Plato, okay, or contributed to, say, Pythagoras. Does that make sense? So some of those kind of maybe something nowadays, like lawyers have these people, they're called underwriters, okay, where like the lawyer gets the credit, but they got a bunch of like kind of first tier people working underneath them that don't get credit for the total work. Does that make sense? Okay. You guys go watch recently all the speeches that congressmen have been making with the whole impeachment process. Okay, not a single one of those speeches that one of those people read, okay, whether it be a Republican or a Democrat or whatever, okay, when they get on the floor and they read a speech, they didn't write that speech, okay, they're lawyers in their like subcommittees, and the lawyers that are in that person's kind of field of scope wrote those papers for them. Does that make sense? Wrote those speeches for them. They don't get credit for it, okay, the people that were speaking are the people that get credit for it, but it was written by somebody else. So that's what kind of wants you to understand with a lot of things in mathematics, when something's attached to somebody's name, if you do a little bit of research, maybe that isn't really attached to them or really isn't due to them, okay? So what I'm trying to get at here is Pythagoras, even though we attach this theorem to him, there's a lot of documentation throughout history that this stuff was being used centuries and centuries before he was even alive, okay? So like the Babylonians and the Egyptians, and they were all using a squared plus b squared equals c squared before him, Okay. Now I don't know if he was just the one that actually documented it and put it down in like mathematical context and whatever. If you go through, maybe figure out if you do some of the research, but he gets credit for something that we have been using a long time before him, right? In mathematics, and you go back in just recent history with calculus. Calculus hasn't been around all that long. There's a lot of things in calculus that are named for certain people that were actually stolen by somebody else. Does that make sense? Okay. You guys know who's the owner of Microsoft? Okay, I think he's retired. CEO of Microsoft. Who is it? Who built Microsoft? His name is in this room. Bill Gates. Okay. You guys know that? Okay. Who built Apple? You guys don't know this stuff? Who built Amazon? Are you kidding me? All right, so I need to pick something up and read it every once in a while. All right, so Bill Gates built Microsoft. Steve Jobs, you ever heard of him before? Okay, he built Apple. Okay, there's a third guy named Steve Wozniak. Okay, who was working with him at the same time. So Steve Jobs and Bill Gates were like best friends. Okay, they were working on this stuff in like their mom's basement and garage. And this Wozniak guy trying to create personal computers. Okay, you guys know what MS-DOS is? Okay, so MS-DOS is the coding. You guys have maybe seen, like if I do this on my computer. Let's see here. Command prompts and stuff like that. You guys seen this stuff before? Okay, so this is MS-DOS. This is the underlying building blocks of what we see as users of the computer. But there's coding behind the scenes, and this Windows idea that we can click on a box or an icon and a window pop up is all generated by that MS-DOS coding. Bill Gates stole that from Steve Jobs. That make sense? Okay, and they split. Steve Jobs goes the Apple route, which is a completely different platform than what Bill Gates went with the Microsoft platform. Okay, if you've ever worked on either of those, you know they're a little bit different, right? Some similarities. Wonder why? Maybe it's because they're working together. Okay, but what I want you to understand is that Bill Gates is attributed to, generating this corporation, and was a very intelligent entrepreneur. But he didn't write that stuff. He didn't come up with it. He took it from somebody, right? And that's history is that way. A lot of people that get credited for something, okay, they didn't make it all on their own. They took it from somewhere. Okay, so it happens a lot in mathematics. So Jeff Bezos, you know who Jeff Bezos is? What's the number one website that I can get online and order stuff through? Amazon. Okay, Jeff Bezos started Amazon in his mom's garage selling used textbooks. Okay, and now he's worth like $120 billion, something like that. Okay, he just built a house with $165 million, and he started by selling used textbooks out of his mom's garage. You guys don't know who these are the like influential people in your lives, like that built and structured this society, and you don't know who they are? Like those names ring a bell? Have you heard them before? Okay, all right. You guys know who Donald Trump is?
Yeah.
Okay, all right. Get somewhere. Do you know what Donald Trump is most famous for prior to being the president? The Apprentice.
Trump Tower.
What is Trump Towers? He's a real estate mogul. He bought and sold properties. Okay. Do you guys know who Warren Buffett is? You don't know who Warren Buffett is? Do you guys know what a philanthropist is? Oh my gosh. All right, so Bill Gates now is one of the greatest philanthropists, but Warren Buffett kind of holds that title as like the world's like greatest philanthropist, which basically is a person that takes their money that they've earned and they donate it to other places, right? But Warren Buffett he made his money through insurance companies. Okay, you guys ever heard of ING? Okay, insurance. That's one of his. There's another one. I forget what it starts with. B. Brookshire maybe is like one of his found or companies, businesses. All right. So these are people that you guys should read things, man. All right. Why is the Pythagorean theorem a squared plus b squared equals c squared? Anybody know? There are actually. Okay, I had the wrong number for the last class. Somebody Google checked me. 367 different true answers to that question. There are 367 known proofs for the Pythagorean theorem. Okay, I'll show you maybe one that makes sense visually. Okay, if I take this triangle, I can do this with any right triangle, and I take the legs, and I just take the leg and say, okay, I'm going to make this leg here, this blue leg, and I'm going to make that the side of a square. Okay, the side of a square. And then, obviously, if the side of the square is 3 units, then the other other side of the square has to be 3 units all the way around. And we should get that blue square. Does that make sense? Do the same thing for the red one, the red leg. Okay, so there's a length of 5. Make a square, then it's 5 by 5. If I were to go through and I were to add up all these unit tiles that exist inside those squares. So what I mean by that is if you were to take that little tile right there, that 1 by 1 tile, that one there, all the way through, there's 9 of them there, right? Count those. Then do the same thing for these. Count all these 1 by 1 squares. And there's going to be, when you do that, 25 of them. Okay? Now what becomes difficult is what happens up here. Now there's some full ones, so there's a full one there. There are some full ones. Okay, so you can kind of get the idea of seeing these full blocks that we could count. But then there are some in here, like let's say that one right there. Okay, but I think if I look at that one there, I could probably kind of attach it to that one, and I get one full one. Does that make sense? If I were able to like just piece that puzzle together of full individual 1 by 1 blocks that were in the green, I would be able to count 34 of them. Okay. Well, what's 9 plus 25? 34. Okay. And that 9 got from taking that 3 and squaring it. This 25 came from taking that 5 and squaring it, okay? And then that 34 actually comes from taking that number there and squaring. So let me give you maybe a better, let's go 4 there, 3, 4, 5 triangle. So that would be 3 squared is 9, 4 squared is 16. There would be 25 full blocks here because 5 squared is 25. Does that make sense? Okay, so that's one approach. I like, merely for what we've been doing, I like this proof. I think this one makes the most sense per the last couple sections. And I'm not showing you remember, I'm not showing you this stuff because I'm going to ask you to remember this. Or duplicate it. I'm showing you to get you guys to realize, to see that these formulas don't just come out of thin air. There's logic and reason behind them. And usually that logic and reason is something that we've been studying, something we've been working on previously that hopefully by itself wasn't all that difficult. Okay? But then making a connection between some things can lead us to new things, new statements and arguments. So I'm going to call this side here A. Call this one B. I'm going to call this hypotenuse over here C. But there are little parts in here of C that I'm going to call D, and that little part E. And that's the picture that we worked with in 7-4 for about 4 or 5 days that said, if you have a right triangle and you draw the altitude from the right angle perpendicular to the opposite side, which would be the hypotenuse, you're going to get some similar triangles here, right? And we taught previously that this segment A is a geometric mean. Would you guys agree with that? So A should go in those two spots in a proportion. Now, what should go, well, what is an option that can go right here in this top numerator, this first numerator? If I'm looking at A as being the geometric mean. Because remember that the leg is the geometric mean between the hypotenuse. So I'm going to put C there. And now, what part of the hypotenuse needs to go down here in the denominator? Part that touches it. Good. So D, right? Everybody okay with that? Remember doing that? Okay. Can I do the same thing for B? Is B another leg? So let's say B is a geometric mean. Now, like Drake said, we could go between the hypotenuse. And now what portion of that hypotenuse is actually touching this purple leg B? E, right? Okay. So we know those two things. Those two things absolutely have to be true because of the similarities in the three triangles that actually exist there. We talked about that back in section 7-4. So if those are true, then we should also know that A squared is equal to CD, right? Just by cross multiplying those two. And we should know that B squared is equal to CE. So those are two things that we should know. Now, if I look at those, that's interesting because I'm trying to get this thing to show A squared plus B squared, right? And right there we got A squared and B squared to show up. All right? But now we've got to do something to get it to be A squared plus B squared. And my question to you is, if I have an equation and I add, let's say, any number I want to the left-hand side of that equation, what do you have to do to the right-hand side? If I'm in the event of either constructing, creating, or solving an equation, if I do one thing to the left-hand side, what do I have to do to the right-hand side? Same exact thing, right? So what I'm going to do right here is I'm going to start with this equation here. I'm going to start with that. And I'm going to add something to the left-hand side. And what I'm going to add is B squared. Okay? Now, if you're writing this, I would not write this next part. But if I added B squared there, what do I have to add to the right-hand side? I have to add B squared to the right-hand side, don't I? Okay? Now, if I look at that, it's interesting because now I've got A squared plus B squared on the left-hand side. That's exactly what I want for my theorem, right? On the right-hand side, I don't have C squared. And if I leave it that way right now, there's no way for me to, with that information the way it's written, generate a C squared. But, didn't this say that B squared was C times E? Does that make sense? So I'm going to, instead of writing B squared on the right-hand side, I'm going to write CE on the right-hand side. And what I want us all to realize is that those two things, though they look different, they're the same amount because it's stated above through the proportion that those two things were equal. Now, looking at the right-hand side, it's a product of two numbers. CD, or it's a sum of two products, I guess is the way I should phrase that. What is common in those two individual products, CD and CE? Remember, these are numbers. Isn't C the same value there as it is there? So can I rewrite this as that? Can I factor that C out and rewrite it as C times the quantity D plus E, right? Does that make sense? Okay. Look at your picture. What's D plus E the same as? It's the same thing as C. That's the segment addition postulate. So don't I get A squared plus B squared, make the substitution that D plus E is the same thing as C. What's C times C? C squared. Okay. So that then is kind of a combination of a geometric and algebraic proof of a squared plus b squared equals c squared. Okay. But this stuff that we're doing here, and this is what you've heard me say this over and over again. That's the math, guys. When we do these problems in a little bit that give you specific numbers and all that kind of stuff, that's practicing this concept. It's doing arithmetic, which is a branch of mathematics. It's a section of it. But why does that work with all those numbers that we give you, and how can we have confidence in those answers? It's because we're using arbitrary values here with these relationships that we know are true, and we get a remark, we get at the end there a statement that is 100% factual. Okay, and that's when we talk about taking an algebra course. That's the algebra. Okay, and it demonstrates then that no matter what I use as A and B were legs. So when we write our Pythagorean theorem, A was a leg, so we'll take a leg squared. B is a leg, so we'll take a leg squared there. And C, if we look at our picture, that was the hypotenuse. So we'll take our hypotenuse and we'll square that. Okay. If you are a person that struggles remembering that C is always your hypotenuse, I think it makes sense to remember your formula as leg squared plus leg squared equals hypotenuse squared. Especially when they give me enough information and they ask me to solve for a leg instead of asking to solve for hypotenuse. Okay. What you guys have done in the past, maybe in 7th grade, 8th grade, last class kind of confirmed this. You guys can tell me if they are absolutely wrong or not. Is you saw questions that were like this. Okay. And they generally ask you, okay, can you find the length of the hypotenuse? Okay. So if this is a right angle, it only works in right triangles. I'm going to say 3 squared plus 4 squared is equal to c squared, right? Okay. That gives me 9 plus 16 is equal to c squared. 25 is equal to c squared. So what's c going to be? My square root. Square root of 25 is 5, right? Okay. That's a special grouping of numbers. 3, 4, and 5. Okay. Because any grouping of 3 numbers doesn't always satisfy the Pythagorean theorem. Okay. 3, 4, and 5 do. And when I say grouping, I'm not sure I say grouping of whole numbers. Okay. So if I give you a number like, let's say 5, 7, and 21. Okay. Well, if I take 5 and square, 7 and square, add together, that does not equal 21 squared. Does that make sense? Okay. Numbers that do that, okay, that do satisfy the Pythagorean theorem, and they're whole numbers, all 3 of them are whole numbers, are categorized as what we call Pythagorean triples. Okay. A grouping of 3 values that are whole numbers that work inside the Pythagorean theorem. Okay. One thing you got to remember when we're looking at seeing if things are Pythagorean triples, and eventually when we're checking to see if the Pythagorean theorem works for a certain set of sides, C always has to be, or my hypotenuse always has to be the biggest value provided, right? Okay. So if you look up here on the whiteboard, I've got a triangle that has 3 and 5 as components. Okay, 3 and 5 as components. Do I know, because 3, 4, 5, we just saw here, if I have 3, 4 as 2 sides, 5 should be the third side of the hypotenuse. So then the argument is, well, if I got 3 and 5 here, can 4 be the hypotenuse there? Why not? Okay, so the hypotenuse has to be larger than 5, therefore it's not. So 3 and 5 don't always guarantee me that 4 is going to be the number that goes with it. When we talk about Pythagorean triples, we're making the argument that the smallest 2 sides are the legs, and then the largest value they give us is the hypotenuse. Does that make sense? Okay. So just be on the lookout for that. There are some common Pythagorean triples that you're going to, I'm not saying memorize these, I would not, okay? But you're going to see maybe enough of these over and over and over again, especially if you end up taking a trig class with me. We see a lot of, just because it makes the process a little bit quicker and easier in homework problems, a lot of times they use these four groupings, 3, 4, 5, 5, 12, 13. So if I look at, 5 squared is 25, 12 squared is 144, 25 plus 144 is 169, which is exactly the same thing as 13 squared. Do the same thing with 8, 15, 17, 7, 24, 25. Last class recognized, and it's true, okay, if I take that first list and double them, so you get 6, 8, and 10. What's 6 squared? 36. What's 8 squared? 64. What's 10 squared? 100, right? What's 36 plus 64? 100, okay? So you can take any one of these groups and multiply it by some n, where I'll just say here n is I'm going to say natural number, okay? So 1, 2, 3, 4, 5, or whatever. And you will get then also another group of Pythagorean triples. So multiply that by 3. So 3 times 3 would be 9, 4 times 3 would be 12, 5 times 3 would be 15. So 9, 12, 15 will be another Pythagorean triple, right? Okay. But these are kind of like the smallest version of those larger groups that we could make. Like I said, I'm not making making you learn those or remember those, but I think after enough exposure, eventually you will recognize those as triples. One thing that I talked about in the last class, and I'm just going to give you guys kind of just so we can get it on the screen here. I'm going to give you a bird's eye view of like a wall that we're building here. Okay, so bird's eye view means we're looking straight down on it, right? Okay. So let's say this is the wall up there with the whiteboard on it, and let's say we've got Lexi's desk right there. Okay. I want to know, is this angle here really 90 degrees? And I'm a contractor, and I want to see if that's 90 degrees, but I've left my protractor maybe in my car or whatever, or at another job site, and I don't have the ability to use that tool. Does that make sense? They sell, you can go to Menards. I have one at home. I might bring it, if I can remember tonight, I'll bring it home, or bring it to school tomorrow. They're essentially, it uses a parallelogram, but I shove this parallelogram into the corner of the wall and make sure the both sides of this parallelogram, because it's able to change the size of it. Okay, it's actually, I think it's a rhombus, which is parallelogram. But I'm able to change the sizes of it, okay, the angles of it, and I set it in this wall and make sure that both sides of that kind of lay against that wall and lay against that wall. And there's a dial on it. It'll point to the measurement of that wall. Okay, but it uses our geometric concepts of parallelograms to do that. Okay, I lost that tool. Can't find it. Okay, I can still figure out if this thing is a right angle by walking down this wall here, maybe a distance of, usually what carpenters will use is a distance of 3 feet. Let me back here. So we'll walk this purple distance, measure that purple distance off as 3 feet, and they'll put a mark on the wall. Okay? Then they'll come to this wall, and they'll mark it off. They'll go 4 feet out. I apologize for that. Keep doing that. I don't know why it does it. So they'll measure out 4 feet. Put a mark on the wall. Then they'll take their tape measure, and they'll measure that distance right there, that dotted line. And if that's a right angle, what should that dotted line on the dot measure to be? 5 feet. Okay? So what a construction or contractor would do is they call it the 3, 4, 5 check. Okay? And it's just making sure that things are perpendicular. Okay? Now you could use, a 6, 8, 10 check. Okay? But 3, 4, 5 makes the most sense for like building homes and that kind of stuff. Okay? So that's kind of where maybe some of this Pythagorean theorem stuff would be used. When we work with these there's going to be some that, a lot of the questions that are going to happen through now to the end of the year, I'm going to ask you to leave them as simplified radicals, okay? We've been talking about this for a while. Let's make sure that we're all on the same page here. If I were to find C, I don't think the process should be difficult. What are my legs? 14 and 9, right? Okay. So 14 squared is 196. 9 squared is 81. So I should get 277 there for C squared, right? When you take, and this is just the algebra, when you take the square root, when you introduce a square root into the problem, it's always a plus or minus that square root, okay? But why can we essentially get rid of the negative root 277 here? Say again? Because it's a length, because we're talking about a physical distance, right? And distances have to be positive numbers, okay? That's something that changes pace a little bit when you get to algebra 2, and we're not talking about distance anymore. You'll keep both answers, okay? The next question is, okay, well, is 277, is that fully simplified? Okay? So we start trying to see, is 277 divide by anything, especially perfect squares, okay? So 277, I believe, is prime, okay? And I know there are no perfect squares that will divide 277, so that one is already fully reduced. And really what we're trying to do there is see when we're reducing, because I know some of you have calculators that do this, which is great, which is fine. But I don't know if I've told the story. When I thought I'd always be able to use a calculator to do work and to maybe help myself figure things out on tests and quizzes and that kind of stuff. I got to college and they told me in my first calculus class that nobody was allowed to use a calculator. Okay? If you took a calculator, brought it out in class, you were removed from the class. Okay? It was effectively cheating, and Bluffton had a no cheating policy, and you were removed. Okay? So you might be in a situation at some point when you have to simplify radicals and you don't have the ability to use a tool that you've always used. So I want you to understand the process here. So 277, if I want to simplify that, okay, I'm going to see if it divides by perfect squares. What I want when I simplify these in perfect squares is I want the number underneath the radical to be a whole number that is either 2 or a whole number bigger than that. Okay? Well, that means I've only got to divide this thing to get a quotient of 2 by 138 and a half or less. Okay, divided by 138 and a half or less. Okay, 277 divided by 138.5 or less will always generate a number bigger than 2. Does that make sense? That's exactly what this is saying here. So I know then that if I've got 277, I'm just going to see if there are perfect squares that will divide it. And I like to work backwards because the idea of simplifying radicals is to find the biggest perfect square. So if I start backwards from the larger perfect squares, the first one I find that divides it will be it. Okay? But if I work from the bottom, if I work with like 4 and 4 divides it, then maybe 16 would have divided it too, right? And ultimately, if 4 and 16 divided, 64 would have been the biggest perfect square that divided it. So I like to work backwards. So I know 138. So I look at 138 and think of, okay, what are perfect squares that are less than 138? Well, I know 144 is pretty close to 138, right? Does anybody know what the square root of 144 is? What number multiplied by itself will give me 144? 12, right? Okay. So that tells me then all I really need to do is see if, because 144 is bigger than 138.5, so I know that's going to give me a number less than 2, so I don't want to try 144. But 12 was the perfect square. So what I want to divide this by 11. Does that make sense? Essentially 11 squared, which would be 121, and see if I get a whole number back. And I don't. So 121 does not divide it. So then I try 10. Obviously 100 was that 10 squared. Doesn't divide it. 9 is 81. Doesn't divide it. Okay. 8 is 64. Doesn't divide it. 49. Nope. 36. Nope. And some of these guys, you know, okay, if it ends in a 6, or sorry, 277 ends in a 7, I know 36 should not divide it because 36 ends in a 7, or sorry, 6. Does that make sense? So I know that these two numbers right here, that 7 and that 6, they don't jive well. So maybe I don't even need to check 36. The next one's 25. Do I really need to check 25? No, because 277, if it's going to be divisible by 25, would have to end in a 5 or a 0, right? So I know some of these are not going to work automatically. 16 again, I know it's not going to work, okay? But just kind of demonstrating, maybe 9. Nope. 4 obviously is not going to work because the 7's not even, right? So none of those things, none of those perfect squares less than 138.5 divided 277. So 277 is already simplified. Does that make sense? And that's kind of obviously when you're doing this on your own, you're not going to be talking and doing all that stuff at the same time, so it's going to be quicker. But that's the approach that we're looking for there. Okay. Kind of scroll down here. We'll do this one here. This is a similar type of question, but now they're asking you to find a leg instead. And this is why I like the formula leg squared plus leg squared equals hypotenuse squared. Because when I get the number one wrong answers, people are going to take 7 squared plus 14 squared equals x squared. Okay? That's leg squared, which is 7, plus your other leg squared, which is x in this case, should equal 14 squared. I don't know why this is the case, but it seems that a lot of sophomores and freshmen, and this has been since I've ever taught, so you go back 13 years, it seems like when we get a formula where the formula sets where one thing is isolated, like in this case c squared is isolated, that they think when they see a problem that the variable in the problem is always going to be that one isolated thing in the equation. And we got to remember that that's not always the case, and a lot of times that's not the case. Okay? So this is a situation where the a squared plus b squared equals c squared, because c is isolated, doesn't mean that c is that variable. Does that make sense? So I'll make sure we're all on the same page with that. So you have 49 plus x squared equals, what's 14 squared? 196, good. We're going to subtract, I want to subtract 50, so it give me 146, right? But when I subtract 50, I subtracted 1 too many, so I'm going to add on that 1 to 146, and I get 147. Square root, right? Okay. And here's the idea. You can do this a couple different ways. But 147, like I said, if I'm trying to simplify that, 147 divided by 2, and you can do this in your head. I think most of us probably could do that in our head. And we get 73. So I'm going to say, okay, well, 147, what's the perfect square that is less than 73? And the first one would be 64, right? So that doesn't work. But the next one would be 49, isn't it? Does that give me a whole number back? So that means to me that 147 is the same thing as root 49 times root 3. But root 49 is the same thing as 7. So there's my value. There's how I simplify that radical. Okay? And that, I think, is the fastest way. You can do this. Some people see this. They say, okay, 147. I know 7 goes into 14 2 times, goes into 7 1 time. This is 7 and 3. And they can say, okay, there's a group of 7s, which would be the 49 that I found. And then the 3 goes underneath the radical. So you can do it that way. Okay? Just make sure, though, that we're looking for the correct component out of the leg, and hypotenuse. All right, so sometimes you're going to ask this question. They're going to say, here are 3 values. Do they come from a right triangle? Here are 3 values. Do they come from a right triangle? So what we're going to be looking for here is taking the information that they give us and putting them in this, okay, and seeing if I get a true statement. So in those numbers, 85, 84, and 13, which one would have to be the hypotenuse if this is a right triangle? 85. So we get 85 squared, and then over here the legs must be 13 and 84. And I believe when you do this, they both turn out to be 72, 25. Is that a true or false statement? It's true. Okay. So if it's true, then yes, it's a right triangle. If it's false, no, right? If it's not a right triangle, what kind of triangles could it be? If it's less than a 90 degree, it's a acute triangle, right? If it's greater than 90 degrees, it's an obtuse triangle, all right? You guys have learned in the past that if I take the formula a squared plus b squared equals c squared, that flows a little bit better than what this does. But I prefer to write my formula as c squared equals a squared plus b squared. Because when they're equal, it gets me a right triangle. When I read this, how do you read that? Less than, right? What kind of angles are less than 90 degree angles? Acute, right? Does that make sense? So if I read this, c squared is less than a squared plus b squared, I put in my values, and that number, that largest number up there squared, is smaller than this sum, I know I have an acute triangle, okay? If I look at it and I plug it in, and this number is greater than 90 is obtuse, right? However, if you were to read this with the a squared plus b squared first, you would read this as a squared plus b squared is greater than c squared. Same statement. So if I read with this stuff first, I get the word greater, and I don't associate greater with acute. Does that make sense? The reason I read this with a c first is because I associate less than 90 with acute, and greater than 90 with obtuse. And that's just maybe a device for helping you decide that. In your homework, they're going to give you 3 numbers, and you're going to have to decide, is it right? Click the button yes or no. If no, then they're going to pop up and say, okay, well, is it acute or is it obtuse? And you have to decide which one of those. Okay? I think that's the best way to decide that. Okay?